Good morning to all. In this video, we are going to discuss the Gray code encoding for the CDC as a solution. So the problem definition is as we discussed earlier in two flops synchronizer. When we transact some signal or data from one domain to another, which is asynchronous to each other, then there will be the setup and hold timing violations. So due to that, at the destination domain may have some uncertain output states, that is called metastability, due to these violations. So to tackle this, there are some certain solutions which can mitigate this metastability problem. So the first one we discuss, the two flops synchronizer. It is for the single bit, and if you want to send some multi-bit, more than one bit, generally people use the Gray code encoding. Before going to start this, we just review what we seen earlier, because it is based on the same two flop synchronizer. So the list of common CDC solutions are, we saw all these things earlier. We go through the two flop synchronizer. Now we are at the second solution, that is Gray code encoding. Later on we see all these things. So the criteria for the solution check, as we have two conditions. One domain is slow and second is fast. At that time the data should be verified, what we send, what we read, or what we received at the destination. Similarly, vice versa, fast to slow, we have to obtain the same data that we sending. This should be satisfied actually, what we seeing that solutions as solutions. So in two flop synchronizer, generally we use two flops at the destination, which is driven by the asynchronous clock B. So it is for the single bit, and it is generally useful for the slow to fast domain, and data will be lost if fast to slow condition is there. So we take case 1 when clock 1 is slow and clock 2 is fast. At that time we seen that we get the what we send. Okay. So similarly, for the opposite case, when clock 1 is fast and destination clock is slow, in that situation the data seem to be lost. Okay. And these are some code for the two flop synchronizer. It is simple as that. These are the test bench for the check. Okay. So at last, what we conclude: slow to fast it will work, fast to slow it won't work. Okay. And if you want to work with fast to slow, we need to do one thing. We have to stretch what we are sending up to the 1.5 times the clock period of the destination. If we do that, obviously we can appropriately get what we are sending. Okay. So the summary is that it will work for the slow to fast. That's okay. For fast to slow, we have a condition: signal length should be greater 1.5 times the clock period of the destination. Okay. So these are the summary for that. And for the overview of what is binary and gray and how many bits are changing there, this simple table is there. We will take the reference of this in further one. In binary, we are saying that there is some changes, one bit change, 2 bit change at value of 2 bits. Then at fourth decimal, we check that the binary has 3 bits consecutive change. But the gray code is one that for any sequential or any gradual, there is only one bit change in the gray code. So it is very useful for low power as well as for the transaction from one domain to another, because we have to only have one bit change rather than the. So why we are discussing this, we will see in a few seconds. So we can transform these two flop synchronizer for the multi-bit. We just have to we just need to bus. We have to change this signal as a bus, and everything goes in spite of the one bit. It will be in a multi-bit like that. But what if there is a conditions occurs? Let's say there are signals. I think in next video we see that. Yes. So in this case, what happened now? There are some multi-bit signals transferring from the one domain, clock A to clock B, and the path that is flowing, let's say for example, from this path the delay is less, and for this path delay is little bit larger. In that case, what happened? The input side is okay, this X, Y is okay, we are getting the rising edge, we transform this signal into proper way. But at destination domain, what happened? The Y1 received as Y2 after this much delay. So at clock B rising edge, what happened? Y2 comes after the clock edge, so it cannot pick by this latch. Okay, so X2 get properly latched. Okay, and Y2 take one more clock to have that correct lock on that. So it means that after all, at this stage we will get that what we required, but it will have the undesired state pass through. Okay, so it means there is some issue with the delay in the path of the bus. We cannot expect some data value with multiple values comes exactly at the same time at the destination. So there will be the path differences, delays are there. So it might happen that one bit come early, next bit may not come at the same time, it will come after some time. Okay, so this delay, due to that delay, the receiver or receiver side latch will not log the same data as we sending. So it will gradually give the correct data, but after some 1 clock or 2 clock like that. So this may create some issues. So to tackle this, we make some decision. We are not sending any multiple bit change. We try our best to conclude that this changes into one bit change. So for that we need one encoder, that is called the gray code encoding. So what we do, we just put one binary to gray here, binary to gray code encoder here, send the multi-bit data, which obviously has only one change bit at any value, and obvious we can have that gray code value here, but we need the binary, so we need again conversion here, gray code to binary. So for the two flops, we cannot use for multi-bits. For the multi-bit, we have to go in this way to avoid this reconvergence or coherence issues. So I hope you got this point, why we are going for the gray code encoding for multi-bit, to avoid this convergence or coherence issues. Basically, these terms used in the CDC in spyglass for the data hold kind of issues are there. Okay, so to begin with this, this concept is used in FIFO also. You see this path for the write pointer and the read pointer. We need to check at the write side as well as the read side these pointers cross way, so that we have to transform this binary to gray here, then flop, and 2 flops, and then again gray to binary. In the same way, in this way also we have to do same thing. So these are the applications where we need pointer values at across the asynchronous clock domains. So for that we have to do these things. Otherwise, it is if we remove these things, it is nothing more than that dual port memory and read write things. Okay, but it is asynchronous. That is why we have to do in this way. So I hope you got this point. So what the pictures comes in like that, we have to add one gray code encoder here. This is binary in gray code encoder, and we have to put the data. Even though there is some delays having differences with each other, but still we get only one bit change here. Okay, so that benefits for the avoiding the undesired state in between the pass through. So it will give proper value at this for the gray. Then we again back to send that into binary, so we have to convert that gray to binary here. So I hope you got this point, and please subscribe my channel and make comments, and please hit like button. So these are the theoretical aspects. Now we are going to do the same on VCS on the basis of the post synthesis coding. So we'll take this. This is our reference design. We do the RTL on it, then synthesize using design vision, and then again check for the VCS simulation with the same test bench. So in that we will see what kind of things happens on the waveforms. So to clarify that, obvious the condition is also same for this one. It will work for the slow to fast. Okay, if you want fast to slow work, then we have to make the signal change here. That should be having the length 1.5 times the clock period of the receiving domain clock period. Okay, so that it will properly latch, or it will have some maximally 3 rising edge events where the data can be picked. Okay, I hope you got the point. In next video we will see actual coding and all these things on the VCS and the design vision. Okay, so that we actually get what we are doing it. Okay, thank you, bye.